In this tutorial, I will explain the most important topic of climate science, multi-model modeling of global climate models. As climate prediction become increasingly important for planning and adaptation, relying on a single model is no longer enough. Each GCM has its own assumptions, limitations, and uncertainties. That's where the ensemble approach comes in. By intelligently combining multiple GCM outputs, we can significantly enhance the accuracy, reliability, and robustness of climate projections. In this tutorial, I will walk through the complete workflow from selecting the right GCMs, pre-processing the data, and applying machine learning techniques like Bayesian Optimization and XGBoost to evaluating performance using hydrological metrics like R-square, root mean square error, and Nash coefficient. Whether you are a climate scientist, hydrologist, or data enthusiast, this tutorial will equip you with the tools to harness AI for more confident climate predictions. So now let's explore the code. Here first you have to import this library in the Colab environment, and then you have to upload the GCM data and the observed data from the Excel file. So as I have already mentioned, you can upload the data from over here. Just click on this one and then select the data file as I have already uploaded. So this is the file, Excel file, which I have uploaded. So basically I will use the top 3 GCM model which were rendered through feature engineering technique in the previous videos. So now we have to highlight the input and target variable. So basically here we have 3 GCM models that are selected through feature engineering technique and the observed data, and then we will fill the missing values, if any, in our data set by using the mean technique. You can use any other technique. So after this we will normalize the data by using minimum maximum scaling techniques. So this piece of code basically will normalize the data. So in the next piece of code, this one, we will divide the data into training and testing. Here I am using 70% data for training the model and 30% for testing. So you can change this value to 0.75 and 0.8 while optimizing the model. So after splitting the data and training and testing, then we will go to the Bayesian optimization. Here I am using grid search algorithm. So in this one I am using an estimator, maximum depth, learning rate, subsample, column sample, by tree. These are different hyperparameters. These are the ranges for each and every hyperparameter. You can change this value based on the literature, and then you have to iterate the data, the model. So here I am using 150 iteration. You can change it. So you can change these parameters value, hyperparameters value, as well as this iteration value to get good result which can be assessed by the statistical performance indicator like R-square, root mean square error, and Nash coefficient, or any other statistical performance which you want to use. So this is basically the refinement of the grid search algorithm. Here you can see in each one they have plus and minus to change its value in this range. So now come to the next one. Here you can see this is the prediction phase, and then it will inverse the scale is in the beginning we have transformed the data using minimum maximum scaling. So by this inverse scale it will retransform the data in its original shape. And these are the statistical performance through which we will assess the model performance. Here I have used Nash coefficient, R square, root mean square error. So once you run the model, then at the end of after completing the simulation, you have to check the value of these statistical performance indicators during training and testing phase. If based on the literature, if these values are satisfactory, is non-satisfactory, so you have to change again the hyperparameter values like these values, and optimize and rerun your model to get the best statistical performance value. And this piece of code is basically for the visualization of the predicted and observed values. So this is basically a time series graph, and this one is graph is used for the residual, and this will show the statistical performance indicator value. So here you can see I have run the model. After once the simulation complete, the R square value during training is 0.35 and testing 0.06. So this is basically non-satisfactory. So you have to change the hyperparameter value again and rerun it. So here you can see also the root mean square error value and Nash coefficient value. So from the literature you can check its value, like the best R square value is if it is near to 1, so the model is performing really good. So here the value is less than very less than 1, because during the training the R square value is 0.35 and testing is 0.05. So the model performance is non-satisfactory. So again you have to change the hyperparameter values to get the good result. And these are the graphics. Here you can see this is the residual graph and this is the time series graph. So you can visualize your results by this one. So here you can see we have used certain hyperparameters like n estimator. So n estimator is the number of boosting rounds, how many trees the model will build. So here I have used from 50 to 200 is the practical range. Too few may underfit, too many can overfit or increase training time unnecessarily. The next one is maximum depth. Control the maximum depth of each decision tree. Low depth, for example 3 to 4, prevent overfitting and keep trees simple. Higher values like 8 allow more complex pattern but might risk overfitting if not balanced. The next one is learning rate. It shrinks the contribution of each tree by a factor. Control how fast the model learns. 0.01 is a slow, stable learning rate, while 0.3 is relatively fast rate. And the next one is subsample, fraction of training sample used per boosting round, also known as raw sampling. 0.5 means 50% of the data is used per tree, adds randomness which reduces overfitting. 1 uses the full data, good for stable large data sets. And the next one is column sample by tree, fraction of features in the columns to consider for each tree, like subsample 0.5 adds randomness by using only half the feature. 1 means all features are considered useful when each GCM is important. So this is basically all about this tutorial.